Yeah, you should definitely know e to the x, sine x, what else? Cosine x. And really, it's also kind of counted 1 plus x to the p. Like, know what the binomial expansion is. If you know those four, you can build an inordinate number. There's one more that you might want to remember. Do you remember? ln x. You might want to remember ln x as well. But those are 5 right there. You should really know. Definitely these. Absolutely really important. And it would be helpful. Okay, so what does it say here? Using known Taylor series, find the first 4 non-zero terms of the Taylor series about 0. Hey, about 0. Nice. Okay, excellent. What's the variable name in this one for number 8? It's z. Not 2, it's z. Nice. So what is this really similar to? Or what could we do to this to actually build this? Anybody have an idea of what we could do? You could integrate it? Okay, so if you integrated this, I like this idea. So you did z over e to the z squared dz. And what did you get when you integrated that? Yeah, what'd you get using u sub? Okay, I like this idea. I like this. Yeah? E to the negative z squared, like this? Is that it? Yeah, if we can test. I'm just doing it in my head real quick. When you do that, you drop the 2z, it becomes positive, and it stays the same up top. Nice. Do people agree with that? Do people agree with? Is that kind of cool?
Not entirely sure how she got there.
How she used u substitution? Okay, let's use u substitution. Let's just do it out then. Okay, sure. So if you use u substitution on this, you let u equal to z squared, correct? Is that what you did right there? So therefore, when you do u substitution on this, you need to do du is going to equal to 2. Why did I put the line through 2?
It's special.
2z dz. So what does dz equal, Matt?
dz equals du over 2z.
Yeah, I like that. Yep. And now we've done the u part, so let's do the substitution part. So doing z over e to the u, and instead of dz, what do we write? du over what? 2z, like this. What's the magical thing that happens right now? The whole point of u substitution is we have to do what right now? What's the nice thing? Things go away. All those 2 z's go away, and you're literally left with the integral of du over, well, 1/2 du over e to the u, like this. So that is 1/2 the integral of e to the negative u du. Do you know how to integrate that? Yeah, you just have to take care of that negative. So that's going to turn into negative 1/2 e to the negative u. But what does u equal, Matt? What did we say u equals?
Z squared.
So this is, you resubstitute and you get negative 1/2 e to the negative z squared. Exactly. So what does that tell us? It tells us when we integrate that thing, we get this right here. Hey, that's kind of cool. Okay. Why is that helpful, Umi? What can we do with this thing right here? You can use substitution on what? On the Taylor series expansion for E. I follow you. Just get all the nouns in there. And I don't mean that facetiously. It's really hard sometimes because these words are long and kind of esoteric. But the idea is we now know what is this thing is going to be equal to. We can just put. Do we really care about that negative 1/2 right there? No. So we can pull that out, and we're talking about this right here. And we just do instead. We know what e to the x is, right? What is e to the x? E to the x is 1 plus what? X plus what? Over plus 3. And it's asking us for the first 3 terms, I think, or 4. What is it asking? First 4. Okay, let's just stop here. So what do we? And it goes on, right? But instead of x, what are we putting in there? Negative z squared, negative z squared, negative z squared. Is everybody with me so far? Okay, that's kind of what we want. This is the integral of what we want it to be, right? So what do we need to do to both sides? Take the derivative. Before you take the derivative, it might help to clean it up a little bit first. So if we clean this up, we end up with 1. Oh, and what else do we need to make sure we multiply by on the outside here? Times what? Close. We need that negative 1/2, right? There's that negative 1/2 along for the ride. Everybody's kind of there? Okay. So what do we have here? Negative 1/2 plus z squared over 2. Is that right? And this is to the 4th, and then it turns negative on the out. It's negative, so we're going to have plus negative what? Z to the what power? Over 4 times over 4. Is that correct? Right? And then we have, oh, are all of these going to be positive? Or excuse me, no, there's going to be negative again. So what's it going to be? It's going to be plus or minus? It's going to be plus Z to the over 12. Is everybody with me so far? Yay? So this is the integral of what we want. So what do we need to do to both sides? This is the integral of what we want. So take the derivative of both sides. Is that legal? Yeah. What were those 3 things we can do to build? We can substitute directly. What else can we do? Differentiate and integrate. We have substitution, differentiation, and integration for primary ways to build Taylor polynomials based on known Taylor polynomials, Taylor series. So we get the derivative. What's it going to be? 0 plus 2z over 2 minus 4z cubed over 4 plus 6z to the 5th over 12 equals z minus z cubed plus z to the 5th over what? 2. Now, unfortunately, what did this question ask us for a final answer? The first how many terms? 4. Did we just lose one of our terms? We did. So what does that mean we're going to have to do, Emily? Yeah, go back up, and you're like, I don't want to do this again. But we know it's at this point we can kind of see it's going to be negative. What's it going to be? Z to the 8th over what? 24? No, not 24. It's going to be 4 factorial times 2. 48, right? Yeah. So we do the derivative of that, and we end up with what? Minus z to the 7th over what? 6. Does that kind of make sense, everybody? So this is the integral of what we want, so what do? Differentiate. That was a really good observation, Umi. Plus z to the 4th over what? 2 factorial?
Yeah.
Plus z to the
6 over
3 factorial, like this?
Yeah.
Now, can you break that up into separate fractions is the thing? No. Yeah, that's the problem there. Like, let me guess. Did you try to do like z over z squared, z over z? Yeah, you can't break things up like a over a plus b does not equal a over a plus a over b. Like, be careful. So nice. Like, you really want it to be?
Can it please?
Can it please? Please, Mr. Seamon, can it please? Lena, go ahead.
Like if you separate it like you said before.
Ah, yeah. So did you? I was wondering if anybody did it this way. Z times e to the negative z squared, like this. And then do you know what e? Can you expand e to the negative z squared? Like, can you do this one right here? Yeah. And then what do you multiply everything by? And does it work? It does. It does. So are there sometimes going to be multiple methods? Absolutely. Absolutely. So this one right here, you know what that expansion is. It expands out, and then you just tack on a z to the outside, and guess what it multiplies to? Right. The same thing. It multiplies to absolutely. Yep, it does.
What about?
It's kind of cool.
Like if you
Was that massive thing with eminent that you need to memorize? What was that thing with eminent? Can someone raise their hand and tell me what it is? Yeah, tell me what it is. The basis for finding error bounds is going to be this right here. Error bounds for Taylor polynomials is that phrase right there. Now, do we know what some of these values are already? Yes, we do. We know that n is going to be, in this case, 3, and a is going to be 0. So we already have m over 4 factorial x to the 4th.
get rid of the absolute value because that's possible.
Exactly. So sure, we could get rid of that if we wanted to, absolutely, and just make it x to the 4th. Okay, cool. So what do we need to find now? What's the mystery thing we need to find? M. Effectively, most of what you're going to be doing is the search for M, right? And do you remember what that phrase was, that inequality you needed to memorize for M? F n plus 1, thanks Cade, of x, right? The nth plus 1 derivative. You want the least upper bound for that. You want the number that you can get, which is the best ceiling, on the interval from what to what. What's the interval that you need to examine? From a all the way to x. What is a in this case? 0. So we're looking at the 0 all the way to x. Now here's the thing. Do we know what x is yet? What is our x value? Be really careful. What is our x value? Someone said it. It's 0.5. Why is it 0.5? Exactly. We want this. We want this thing to be what you get when you plug in the appropriate x value. It just happens to be the same as the number here, right? But for example, let's say that was the number 2. What would the x value be? Yes, that's really important. Does everybody see that really important thing? We want, what do you plug into this to get this? 0.5. Could we change this a little bit and use a 2 right here instead if we wanted to? We could. We could. It would be a different error bound though. But now, what is x going to be? 0.5. So we're going from 0 to, and I'll go back here to, what is it? 1/2? Nice. It's right there. It's literally on the board. F of x is equal to 1 minus x to the what power? 1/3. That's an F. It was just, the pen slid. Okay. So what do we now need to do? Differentiate. Exciting. Differentiate. Isn't it really exciting? Or it's not exciting? Okay. So the only challenge here is what are you going to have to keep track of? Negatives and some fractions. And you get a little sad, but here, is the process changing at all? No. Yesterday we did this process with the nicest function imaginable, which was e to the x. Now, what did I very clearly tell you? It's going to get a little bit more messy. Exactly, right. But it's not that bad. What's f prime of x going to be? Negative 1/3, 1 minus x to the what? Yeah, but then the negative comes out. I'm doing the chain rule at the same time. Sorry, negative what? 2/3. Is that correct? Because you subtract 1? Please don't let me make a mistake on this, okay? Please. That's one of your responsibilities as a class. You're my spot checkers, okay? So then we have f, the second derivative, and what's that going to be? Negative 2/9. Thank you. 1 minus x to the what? Negative what? 5/3? Do we have all the signs taken? Because it turns positive and goes back again, right? And it's going to stay negative, right? Because we're going to keep on dropping negatives, but then it kicks out a negative. So f, the third, is going to be what? Negative 10 over 27? 1 minus x to the what? Negative 8/3? Is that right? And then f4 of x is going to be negative what? 80 over 81? 1 minus x to the what? Negative 11 over 3. Nice. So just, so now what we're looking for, what's the least upper bound for that function on this interval right here? 0 to what? Why 0 to 1/2? Because 1/2 is what we're plugging in, and the theorem says you look for the largest value of the n plus 1 derivative from a to x. From a to x. So this function, right now you have to do a little bit of analysis, because this could absolutely be a non-calculator question. You have to look at this and say, how do we make that largest from 0 to? But I would like to rewrite this a little bit, and let me move this down a little bit here. Hold on. Give us a little bit more. I would rewrite it as, so we know f4x negative 80 over 81 times what? 1 over what? The 11th, sorry, no, the third root, excuse me, right? The cube root of 1 minus x all to the what? 11th power. The real question is, how do we make that as big as possible? How do we make that as big as possible? Yeah, it's going to be x is 0.5. It's going to be 0.5. It is biggest when x is equal to 1/2. So now, what do we plug into there? We plug in 1/2, and what do we have to actually simplify a little bit of, please? Yeah, it's not the best. Like, so when you're simplifying this, you get 80 over 81, and then you get 1 over the cube root, like 2 to the. It's 2. Well, it's 1/2, right? Yeah. So 1/2 to the 1/3 to the what? 11th, right? So I mean, you just have to be really careful about it. It's 80 over 81 times, what do we got? 1/2 to the 11/3 power, right? So that's 2 to the what power? That's 2 to the 11/3 power. Are we there so far? We're not bad. So this right here And we are right. I'm just tracking. I want to make sure we were really okay on this. We are tracking this okay. That's just the m value, everybody. That's just the m value. So the real question is, where do we plug that in now? Do you remember where we plugged this in? How did we get 2? Because it flips over. Like if we flip this over, look. If we flip this over, it becomes negative, right? But then if we bring it to the numerator, what does it become? The power becomes what? Positive. If you translate across, it becomes positive. I'm just doing a bunch of simplification all at once to save us a little bit of sanity and hoping we don't make a critical mistake. Of all the things I've lost, I miss my mind the most. Okay, so we've said that m is equal to this thing right here. That's Ozzy Osbourne, not Mr. Seamon. But now what do we have to plug that into? Do you remember our original statement right here? Hey, we already had this, right? So we take this, and where do we plug it in? Oh, this is exciting, isn't it? Yay, m goes right there. And what was x equal to? We said x was 0.5. That's what we needed to plug in. So what do we have here? We have 80 times 2 to, not 20, that would change the answer a lot. 2 to the 11/3 times 1/2 to the 4th, all over, what's 4 factorial? Times 81. Woo! I'm going to shade things so you can track where they're coming from. Here is our m value. Right here, 80, 81, and this right here. You with me so far? What does this represent right here? What is this? That's the what? That's the x to the 4th, and this right here is the 4 factorial. Two things about this. First of all, on the AP exam, how many decimal places do you go to? 3. You have to go to 3. If you don't go to 3, you don't get the answer point. How many points are there total on the BC Calculus exam? Same as the number on the AB exam. Remember how many points there are?
2.
108. There are 108 points. How many of them do you need to get a 5, generally speaking? Around 68 to 70. It changes a little bit every year. The cut points change. But generally speaking, you need about a 68 to 70%. So around a 70, 72 to get a 5. That being said, so that seems like oh man, that's not, it's because it's a challenging test. But the takeaway I want you to take is 1 point really, is a point a point? Yes. One of the easiest ways to lose a point would be to write an answer like, if they asked you what the error bound is, if this was a calculator section, you would write it like this. You wouldn't get the answer point. You would get the point for all the work, which would maybe multiple points, but losing that answer point, take it easy. So that's correct. It keeps going, right? It's pretty nasty decimal, right? What would you write it down as? 0. What? 033. Exactly. That's what they would accept right here. This is what you'd want. So this right here is the estimated error bound that we found. But what does the question ask us to actually do at the end here? It asks us to do what? With the what? Actual error. How do you calculate the actual error? Yeah, the actual error is the absolute value of f of x minus the Taylor polynomial approximation, right? What was the function we're dealing with? Do you remember? It's 1 minus x to the what? 1/3. 1/3, right? And then what do we need? What degree polynomial are we going to here? 3rd degree, right? So we need to find the 3rd degree polynomial, and that would be this is the actual error. The actual error. This is the maximum error that we calculated using a shorter method. But if we wanted the actual error, we would need to find out. We're not going to do it right now. You need to generate the first 3 terms, or to the 3rd degree, right? So it's 4 terms. Or maybe just go to 3rd degree. Some of them are zeros, maybe, right? And then you have to plug in 1/2. If you do this, so if you find E3, so that's the error 3 of this polynomial, and you're doing it at, let me get this right decimal here, E3 is going to be, you end up with negative 0.00414. What's interesting about that error compared to this error? So this was our estimated error. This is our estimated max error. What's interesting about this one compared to this one? The sign is different, but that's actually okay. It's absolute value. But what? It's not what? I can't hear you. It's not to 3 decimal places. Can you tell me how they relatively compare to each other? That's way bigger, relatively speaking. It's just an observation to make. The error on our estimate was way bigger than the actual error. Correct. what are we going to do? What's that phrase you need to remember? Someone raised their hand and that's Umi. What is it? M over.
M over n plus 1 factorial.
Yep.
Times x to the n plus 1.
X minus a to the plus 1. In this case, start chipping away with what you know. What do you know n is in this case? 4. What does a equal in this case? No, it's 0. What does it tell you? It's about what? It says about x equals 0. Is that, well, that's kind of nice, right? So what do we now have? We have m over what factorial? 5 factorial x to the what power? Okay, we need to keep that absolute value in. X to the 5th. Exactly. Right. That's nice. Now, what is our x value? What value are we plugging in for x? You already know x. Yes? I don't know why that came up. Go away. There we go.
It just wants to be one.
It wants to be, yeah. X is equal to 1/4. So we plug that in, and what do we have here? M over 5 factorial, and we can get rid of the absolute value now, right? 1/4 to the 5th. We've done 50% of this problem already without actually having to calculate anything. All we're doing right now, this is just a test of the comprehension of the concept. Now, the other 50% is needed. Now we're on the quest for what? M. We're on the quest for M. And what do we know? F n plus 1 on the interval has to be less than or equal to M, right? What did they give us a picture of? They gave us what we want, which is, this is 5, right? We have the picture. And what is x? 1 over 4. Is everybody with me so far? Oh, did they nicely give us something that has a quarter marked on it? Yeah, so where's a quarter? Right there, right? Now here's the thing. We want to know numbers that are definitely greater. Can you give me a number that is definitely greater than this evaluated at 1/4? 40. We know, and why are we choosing that specifically? We're trying to compare it to something that maybe we need to be able to simplify. This is not a calculator question. So what are we going to say m is equal to? 40. So where do we plug that 40 in? We found out what m is. Where do we plug the 40 in? Yeah, we take this number right here, and we plug it in right there. So what do we end up with? 40 over 120 over 1 over 4 to the what? 4 to the 5th. Oh man, what do I do with this? Cancel what you know. Well, you know that's 10 times 4 over 120 times 4 to the 4th, right? You see how I expanded it right there? Do things start canceling? Yeah. So what do I, oh, this cancels and this becomes a what? 12. So what is this? 1 over 12 times what? 4 to the 4th. And this right here. How does that compare to 1 over 3,000? Anybody remember what 4 to the 4th is? Is it 256? Who agrees? 16 times 16 is 256. Remember I said I did sometimes do basic multiplication? Is everybody with me so far? Okay, here we go. Is everybody with me so far? Okay, so we know that this is equal to 1 over 12 times 256. And you're like, oh man, I'm totally stuck here. What do I do? You might actually have to do some multiplication, right? Well, that's actually going to be 2,560 plus 256 plus 256, right? You see how I broke that up? 12 is the same thing as multiply something times 10 and then 2 of it. I'm showing you what goes on in my head. Maybe it'll match something that you want to do with your life, maybe, right? So this is the same thing as 2,560 plus 512. So that's 27103. So what do we show this is? Right. So our error bound right here is 1 over 3,072, right? But what is that compared to this? We just showed that the error bound we got is smaller than that 3,000. So therefore, is the error bound definitely less than this? We just show it has to be below here. How does that compare to here? Definitely has to. Our answer is below 3. Is it also below 5? Yes. Sometimes, yeah. So when you get questions that specifically don't require a calculator, make sure you don't do things that require a calculator. Sit down.